Hello, my name's Julian Edgar and I'm the author of the book Custom Air Suspension. It's on how you can fit a custom air suspension system to your car. But today I don't want to talk about air suspension as such. I want to talk about a parameter that can apply to any suspension system, and that parameter is natural frequency. Now, I've already done a whole video on what natural frequency in suspension actually is, and so if you're not sure, obviously go and check that video as well. But in short, it's a measurement of how stiff or how soft the suspension is. It takes into account spring rate, it takes into account the load working through the spring, it takes into account motion ratio, the leverage ratio of the arm over the spring, it takes into account all of those things and gives you a measurement at the wheel of the stiffness or softness of the suspension. Now, frequency is normally measured in hertz, a number of cycles per second, and cycles per second is a really good way of thinking of suspension. If you have suspension which is fairly stiff, say a sports car, and you push the suspension down and release it, it'll want to bounce, it'll be damped, but it'll want to bounce at about 2 hertz, twice a second. That's a fairly stiff suspension system. Or you can actually try pushing it up and down, and that's the frequency it'll want to bounce at. What about a luxury car? Well, a luxury car, say a car with air suspension, will have a natural frequency of about half that, of about 1 hertz. It'll want to bounce up and down about once per second. So the natural frequency is a real-world indicator of the stiffness of the suspension, and that's why all suspension textbooks, high-level suspension textbooks, all vehicle dynamics textbooks, they never talk about spring rates, they talk about natural frequency. Interesting, but so what? Well, the really interesting thing is over the last few years, this whole area has been transformed from a point of view of an amateur working on their own car. And it's been transformed because of the release of certain phone apps. If you have a smartphone, you can actually directly measure the natural frequency of your car. And you can measure the front natural frequency, you can measure the back natural frequency, both in bounce, but you can also measure the natural frequency of the car in pitch, and you can also measure the natural frequency of the car in roll, and all of those comparisons, all of those measurements can be used to compare your car with other cars, or can be used when you're actually designing the suspension. You know, what natural frequency am I actually aiming at? So, a smartphone has the ability to directly measure natural frequency of the car. Now I want to look at one of those apps. It's on an Apple operating system. I understand Android ones are also available, but I've only used the Apple one. And it's an app called Vibration. And Vibration, it's very, very cheap, $4 or $5 US to buy the app, and it can measure natural frequency of your car in all of those different directions, bounce, roll and pitch, very, very accurately. So I'm going to take you through some of the functions of that Vibration app now. Like all software, it's easiest just to actually try it and play with it and get to know it, and then you'll find it quite easy to use. Going through every single thing, which I'm not going to do, but that tends to take a lot longer. So let's have a look at the app, and I've got it here on my phone. So if we bring it up, we go to settings, we've got data source, you select the internal accelerometer. We've got data acquisition settings, put in a little sample delay, maybe a few seconds, and then load it in terms of the sample length that you want to sample over, say 10 seconds, that's fine. If you go back to, again, triggering, don't worry about that. Display settings, you probably don't even have to worry about that now, except here is one that you can be concerned about. Have a vertical scale of 0.2 G, a scale multiplier of 1, and so on. But the really exciting thing is when you have the phone, you put it in the car and you start bouncing the car up and down. Now, bouncing the car up and down might need 2 people working in concert. You soon get the idea of how to do it. It's just like pushing a child's swing. You always know when to push, don't you? Because if you push at the wrong time, you can feel the resistance is much, much greater. It's the same when you're bouncing one end of the car. So you put the phone across the axle line at one end of the car, you start to bounce it, and then you press the sample button. And it's bouncing up and down like that. It's recording the bounces up and down as I'm doing. Fairly big bounces here, it's not normally as great. And it's drawing the graph as we actually speak. And then after 10 seconds it makes a beep, and we have a series of graphs that have been drawn on the phone. Now, those three graphs are for different directions of motion, but we're only interested in the one that's going up and down, and that will have the greatest amplitude, the biggest peaks and troughs. And so we've drawn a graph of the acceleration of the car up and down as it's been bouncing. Now, here's the really extraordinary step that this software allows you to do, which in the past would have taken tens of thousands of dollars of really complex gear. What you want to do is you want the application to find what was the most common frequency in those bumps up and down. Because there'll be a whole bunch of different frequencies in there, but which is the one that really stands out, because that's the natural frequency of the system. And the way we do that is we just go to frequency. And when we go to frequency, we can see that all the different frequencies have been shown. We move the cursor across to the highest peak, which I'm just doing now, and in this case, when I was just bouncing it by hand, the highest peak is at 1.9 hertz, so fairly stiff. That would have been the same sort of bounce rate that you would have got in a suspension. So by doing that, and doing it in the real world takes a lot less time than my describing of it, by doing that we can measure directly the natural frequency of each end of the car in bounce. And then if we want to, we can do it in pitch. You need 2 people or 4 people if you're working to work out pitch. 2 at each end, bouncing like that, okay? So pushing it at opposite ends, out of phase if you like. And to do it in roll, what I find is easiest is to open the doors, one each side, and get people to stand on the sill panel so the car's going like that. Now, you might say, well, so what? That's all very well and good, and it is well and good because it really makes you understand natural frequency as it's described in the textbook so much better. But to give you an idea, the front and rear natural frequencies should not be the same. They should not be the same if you want the car to ride level across big bumps. And when you do an analysis of any production car, you'll find that the front and rear natural frequencies are not the same in order to achieve that. Now, if you want to go into more detail, and maybe I'll cover this in another video, there's actually a proportional relationship between the front and the rear natural frequencies to achieve a flat ride. There's at least one car I see on the road quite a lot where the engineers got that completely wrong, and you see it porpoise like that whenever it goes over a discrete bump. It's fascinating because you can just see the engineers completely forgot about the relationship between front and rear natural frequencies. European cars, on the other hand, tend to be very, very good in that respect. But here's another interesting aspect of that. The tuning of the front and rear natural frequencies and their relationship is also dependent on how fast the car is being driven. In other words, the time delay between the front axle passing and the rear axle passing. And my wife recently bought a 7 or 8 year old Mercedes, and I can clearly feel how the pitching behaviour changes. At 130 kilometres an hour, it's far, far better at pitching. It doesn't pitch at all compared with, say, 80 kilometres an hour going over the same bump. And that's because the relationship between the natural frequencies has been designed. So they expect the car to be doing 130 or more down the road. I find it really, really interesting. It's a fascinating way of finding out what your car suspension is doing. It's a fascinating way of finding out what changes you create by changing springs in air suspension cars. And remember, that was where I started today's video. In air suspension cars, it allows you to actually measure natural frequency, which otherwise is very difficult to do when you've got non-linear springs. A really interesting area, and grab a smartphone, grab an app that can measure vibration and have a play. I think you'll find it very, very interesting indeed. Thank you.